For the past 9 minutes, the space shuttle has been powering its way through the atmosphere, propelled forward by 2 massive solid rocket boosters. Completing their duties 2 minutes into the flight, they are now falling back to Earth, where they will be refurbished and reused. The final push comes from the orbiter's 3 main engines, being fed liquid oxygen and liquid hydrogen from the colossal orange external tank at an astonishing rate. Having drained the 700 tons of fuel and oxidizer from its tanks, the time has come to shut down the powerful main engines and jettison the external tank. The astronauts inside the orbiter will find themselves transitioning from an exhilarating, thundering journey to a serene, silent cruise, becoming weightless the moment the engines power down. The light of the shining blue Earth below them flood through the windows of the crew cabin. The journey to orbit has ended, but their mission has just begun. The space shuttle was not just a rocket, it was a mobile laboratory, a home in space, and it came with all the tools the astronauts needed to not just survive, but to complete complicated tasks in space. A sanctuary amidst the unforgiving expanse of space, the orbiter provided a secure haven, sustaining a breathable atmosphere, facilitating precise maneuvers, a payload bay capable of carrying massive spacecraft like the Hubble Space Telescope, and the machinery needed to repair them when needed. This is the insane engineering of the Space Shuttle Orbiter. The astronauts' jobs begin the moment they reach orbit. The orbiter has released the external tank, and it's beginning its journey back through the atmosphere, where it will disintegrate. This is the last view anyone will have of the external tank intact, and it was vital that photos of it were taken to check for any issues that could have occurred on ascent. To do this, the commander of the orbiter needs to pitch the shuttle onto its back using its maneuvering system. Scattered all over the orbiter are smaller rocket nozzles, part of the reaction control system. This removable module in the nose of the aircraft was the forward reaction control system. Inside, there are 2 spherical tanks, an oxidizer tank filled with nitrogen tetroxide and a fuel tank filled with monometal hydrazine. This fuel oxidizer combination is unique. It doesn't need an ignition source. It's hypergolic, meaning they spontaneously ignite upon contact with each other. But both substances were extremely toxic, producing ominous orange clouds of toxic gas. Breathing this in would cause your lungs to rapidly fill with fluid, and once in your bloodstream, it interferes with the blood's ability to carry oxygen. Anyone working with these propellants had to wear pressurized breathing suits to prevent any chance of contact. The astronauts also had exclusion zones around these nozzles on spacewalks to prevent any danger of the chemicals coming back aboard. It's an undesirable fuel to work with in many ways, but its advantages were why it was used. These hypergolic fuels were extremely reliable. Igniting on contact with each other removed any need for complicated ignition systems that could fail. They could be stored for longer periods than cryogenic fuels that would have to be continually vented as temperatures rose, which makes cryogenic fuels unsuitable for longer missions like the Space Shuttle. With the longest Space Shuttle mission lasting 18 days, this was critical. The propellants could also be quickly mixed in precise volumes to provide precise and instantaneous thrust control. This was important when maneuvering in close proximity to another spacecraft. The propellants are fed into the combustion chamber through pressurization of the tanks with high-pressure helium, held in spherical Kevlar composite tanks with titanium inner liners. An extremely lightweight tank, just 10 kilograms in weight, but nearly a half-meter in diameter. Spherical tanks are the most weight-efficient form of pressure vessel, with the highest volume-to-weight ratio. Ideally, all rockets could use spherical tanks, but ultimately, diameters increase too much as volume requirements rise, and it's preferable to minimize the cross-sectional area of the rocket to reduce drag. There is no turbopump needed here. The back pressure from the high-pressure helium provides enough flow rate for the purposes of these low-power rocket motors. In the forward reaction control system pod, there are 12 main thrusters, and there are 12 in each of the left and right rear pods too, for a total of 38 main thrusters, each capable of providing 3,870 newtons of thrust with a specific impulse of 289 seconds. Sometimes even finer control was needed for delicate docking procedures. And for this, the orbiter had 6 smaller vernier thrusters, capable of producing as little as 111 newtons, the same amount of force you would need to lift an 11-kilogram weight here on Earth. With a total of 44 reaction-control thrusters scattered around the orbiter, the astronauts needed a way to control them. The controls were located at the commander's seat on the left side of the cockpit and here on the left side of the aft flight deck. The rear position was added to allow the commander to look out this rear window while maneuvering for rendezvous with other spacecraft or releasing payloads. Each station had a square-knob controller used for translational movements, in and out, side to side, and up and down, and a more traditional flight stick, which was used to control attitude, pitch, roll, and yaw. There was also a flight computer where desired altitude and velocity changes could be entered with a keypad. Of course, this was all fly-by-wire. The commander's inputs were all fed into a computer, which interpreted the commands and decided the best course of action. There was only one notable exception for this fly-by-wire system.
I mean, there is nothing mechanically linked to any of the control surfaces or anything. Everything goes through the computer. Everything you touch goes through the computer, and the computer generates everything. We're concerned about things called single-event upset. You've probably heard of those before, where a cosmic ray comes in and upsets the computers, and you can recover from anything. But because there is no way to raise the landing gear, we are concerned a single-event upset, if there is an automatic computer's way to lower the wheels, that you can get your wheels lowered on orbit and not be able to come home. So we always made that mechanical, and so once we got down to under 300 feet, 200 feet, that was the pilot's main job, was to lower the wheels manually.
Putting them back in place required ground crew to push them back in. So, because ionizing radiation in space could potentially trigger the computers to lower the landing gear, and with no way of raising them back up, they were lowered manually. The landing gears were held in place by a hooked lock that was released after the pilot flipped the protective covers on these 2 buttons, an arming button and a button labeled DN for down. When this happened, a hydraulic actuator released the hook, holding the landing gears in place and allowed them to lower. The first day of the mission is now starting. The astronauts begin their tasks. The pilot and commander, seated in the left and right seats in front of the instrument panel, are busy working towards the first rendezvous with Intelsat. Through the forward windows, the astronauts can glimpse a distant bright dot, the satellite they are maneuvering towards. These weren't the only windows on board. There were additional overhead windows, along with rear windows looking into the payload bay, which for now remains closed. These windows were key to the reusability of the shuttle. The windows had to be durable enough to survive space debris impacts and capable of resisting the temperatures of re-entry. The Space Shuttle's window structure had multiple layers of glass, each tailored to withstand different conditions. The pressure pane was engineered to endure the cabin pressure in space. It was made from 15.7mm thick aluminosilicate glass that was tempered to be mechanically strong. On the outer edge of this pane, a red film was added to reflect back the heat into the vehicle so it wasn't lost to space, while still letting visible light through. The outermost pane, or the thermal pane, was also 15.7mm thick and capable of resisting temperatures of up to 482 degrees Celsius. There was also a large space between these 2 panes, which minimized heat transfer between the outer shell and the inner crew cabin. On one Discovery mission, one of these windows was struck by space debris, leaving a small crater in the window, but it did not break. If it had, the astronauts inside were in no danger, as there was also a center redundant pane, serving as a failsafe for both the thermal and pressure panes. It was 33mm thick and made out of fused silica glass, the same material that laboratory crucibles and beakers are made out of. The rear windows, looking into the payload bay, did not have the outer thermal pane, since they would not be exposed to the extreme superheated plasma during re-entry. There were no windows in the middeck below the crew deck. The middeck is where many of the science experiments in orbit were performed, and this is where the astronauts slept and ate. There were stations where the astronauts could strap themselves to the walls in the weightless environment, but not everyone chose to use them.
The commander and pilot generally slept up on the flight deck. They would just loosely strap themselves in their, commander and pilot seats. that was a good way. And you want to be kind of strapped in. There were some astronauts like Story Musgrave that liked to free float around in space, but he would bump into people, and I heard that it was quite annoying sometimes. But the rest of us, you have a cloth sleeping bag that's made out of just light material like this, where you Velcro it to a bulkhead or the ceiling, and you just zip yourself up in it.
The time has now come to open the payload doors. The doors needed to be opened shortly after reaching orbit, as one of the Space Shuttle's vital life support systems required them to be open, the temperature control system. 2 radiator panels are attached to each of the forward payload bay doors. Freon-filled tubes snake around these panels, where they radiate heat absorbed from a heat exchanger located inside the orbiter into space. The payload doors themselves are made from a graphite epoxy composite material, which reduced the weight of the doors by 408 kilograms over a comparable aluminium design. At the time, this was the largest aerospace composite structure ever made. Covering the payload bay, which was 18.3 meters long and 4.6 meters wide. The largest and heaviest payload it ever carried was on STS-93, with the Chandra X-ray Observatory coming in at 22.7 tons, maxing out the shuttle's capacity. This mission came worryingly close to disaster. During each refurbishment of the shuttle's main engines, they were inspected with ultrasound to find signs of damage. In some cases, damage may be detected in one of the liquid oxygen posts that delivered liquid oxygen to the combustion chamber, and instead of replacing the entire expensive and difficult to manufacture injection assembly, the post was simply deactivated with a gold pin that plugged the channel. During the pre-launch startup sequence of the main engines on STS-93, one of these gold pins was ejected out and struck the hydrogen coolant channels in the nozzle, resulting in a hydrogen leak that you can actually see here in images of the launch. The engine detected a decrease in combustion chamber pressure and opened the oxidizer valve to increase thrust. The engine had no way of knowing the issue was a hydrogen leak. It could only detect the drop in combustion chamber pressure and respond by making the combustion less fuel-rich, which increases thrust and temperature. This incident resulted in a maintenance policy switch that meant damaged oxygen posts had to be replaced and not simply plugged. Thankfully, the engine survived, and the mission was successfully completed, despite the main engines shutting down prematurely as a result of the oxygen depletion sensors being triggered. So, the orbiter was 4.6 meters per second off its target orbital velocity. Thankfully, the orbiter had an orbital maneuvering system that could bring it up to its desired velocity. These large rocket nozzles were not part of the reaction control system and were capable of providing 305 meters per second of additional velocity, powered by the same hypergolic fuel and oxidizer as the RCS system, from tanks hidden within the OMS pods, capable of holding 4 tons of fuel and 6.7 tons of oxidizer. When performing large orbital changes like this, it was important for the space shuttle to know precisely where it was. And to do this, it could open these doors on the left side of the orbiter's nose, revealing the star tracker optics. These star trackers analyzed known positions of the stars in the sky to determine exactly where the orbiter was, allowing it to precisely navigate in orbit. Once the space shuttle has arrived at its target orbit, the real work can begin. On Bruce's mission, STS-49, the first task was to rendezvous with that stranded communication satellite, carefully maneuvering the orbiter closer to the satellite as the satellite's operators attempted to stabilize its spin. As they approached, 2 astronauts, Pierre II and Richard Heeb, donned their EVA suits in the middeck and prepared to enter the airlock. The airlock for this mission was located inside the crew cabin of the middeck, but it could be configured to be outside in the payload area. During the construction of the International Space Station, a special docking system was also installed, which was required to allow the Space Shuttle to dock to both Russian and American spacecraft. It was called the Androgynous Peripheral Attach System. The androgynous name comes from the fact that both the target and the receiving end look identical, with no male or female parts, with the goal of this being a universal docking system, allowing any 2 spacecraft to dock together, as Goddard intended. Each side had a ring with 3 petals equally distributed. One side extended its mating ring for a soft capture, where the 3 petals of each side come together and connect with these latches. At this point, the soft capture ring is retracted and 12 latches engage to form an airtight connection between the 2 spacecraft. This system was used extensively during the construction of the International Space Station, which the Space Shuttle had an instrumental role in transporting and assembling in space, including the very first modules to be connected in 1998 on STS-88, when the orbiter docked with the Russian Zarya module using this docking ring and proceeded to connect the Unity module. On STS-49, Bruce's mission, the stranded satellite was never intended to be docked with and had no docking points, and thus, to capture the stranded satellite, the astronauts needed to perform an EVA and manually grab the satellite using a capture bar specifically designed for this mission, but not everything went to plan.
So we made several attempts to grab this satellite with the capture bar, but every time Pierre touched the bottom of the satellite with the capture bar, it bounced off out of control. Fortunately, the engineers that owned Intelsat, they could send commands back up to it, restabilize it so we could maneuver back closer to it and try again. So we tried 3 or 4 times the first day to grab it, every time it bounced off. Second day we tried again, every time it bounced off. So at that point, we were kind of at a loss. We didn't know what we were going to do. And of course, all this time, I'm operating the arm. I'm chasing the satellite with Pierre on the end of it. And so it was a very demanding part of the flight. So after 2 days of trying, the ground said, okay, we're going to take the 3rd day off. And then we'll go back out and try on the 4th day to do it again. Well, of course, we felt like the mission was lost. So, the ground told us, go ahead, get a good night's sleep, we'll call you in the morning. So we got to thinking. As a matter of fact, I saw that I could hear that Dan and Chili were talking up on the flight deck. We were supposed to be asleep. So I floated up to the flight deck with them, and they were talking about how Endeavour was so maneuverable and was so efficient on its fuel burn that they thought we could get close enough to the satellite to where Rick and Pierre could just grab it with their gloved hands. And we saw it at one point when Pierre got the capture bar, one side of the capture bar fired, and it almost immediately stopped the rotation. So we knew that it was going to be easy to stop the rotation if Rick and Pierre could just grab the bottom of the satellite. The problem is now what do? If you do grab the satellite, you've got 2 guys out there holding a 9,000-pound satellite with no way to get it back on the rocket motor that we took up to strap to it, send it back up to the proper orbit. Well, I scratched my head while I was up there, and I knew that because after we finished the satellite business, 2 other astronauts, Tom Akers and Kathy Thornton, they were going to go out and do some practice of assembly of the space station. We hadn't built the space station at that point, and they were going to be out trying to do some methods for that. Well, in order to accommodate all the different sized astronauts, the EVA suits, or the spacewalking suits, they're made out of different components, different length arms, different sized torsos, those sorts of things. And Rick Heeb is this big, Kathy Thornton was this tall, and then Tom and Pierre are about my size. So in order to accommodate 4 astronauts on 2 different spacewalks of those different sizes, we, for the first time ever, had 3 full EVA suits, the components of 3 full EVA suits on board. So I got to thinking, I said, well, we have 3 suits on board, why don't we send 3 spacewalkers out? We can have 2 people grab it and then 1 person put the capture bar on, because the capture bar had to be attached to the satellite because that was what was going to attach it to the rocket motor that we brought up.
However, this plan had one problem. The airlock was only designed for 2 people. The airlock consisted of 2 airtight doors. Once inside, with the door sealed, the astronauts could depressurize the inside by venting the air to space. This could only be done from inside the hatch, but repressurization could be done from outside and inside, for obvious safety reasons. This process took about 30 minutes, and while it happened, the astronauts were connected to life support umbilicals so that they didn't have to waste their internal supplies during the wait. This was the first problem. there were only 2 life support umbilicals available. It was also going to be a tight squeeze for 3 astronauts with full EVA gear on, as the cylindrical airlock inside the deck was just 160 centimeters in diameter and 210 centimeters high. The 3rd astronaut was going to need to make some sacrifices.
So unlike normally where you just have 2 astronauts, you put them in the airlock, you close the door, with Tom, he had to go on all of his internal controls, and we float him in the airlock upside down. So now you've got Rick and Pierre right side up and Tom Akers head down in the airlock, and he's on his internal systems now where Rick and Pierre are still attached to the umbilicals inside. Close the airlock, evacuate it, and then all 3 of them floated out.
And here, the 3 astronauts got to work, with Bruce on the remote manipulator arm controls inside the orbiter, and he was chosen for a very specific reason. He was a Coast Guard helicopter pilot.
And the reason, Dan wanted to have a Coast Guard helicopter pilot on the arm. And the reason for that is that operating the arm, the controls that you use are vaguely similar to operating a helicopter, because in a helicopter, you have to fly with both hands and both feet. Well, when you're operating the arm, you've got 2 controllers. You've got a rotational hand controller and a translational hand controller. So the translational hand controller, you move up, down, sideways, in and out. Rotational hand controller controls the attitude of the arm. So it's very much like flying a helicopter. And you can't be thinking about it when you're in a very, tight situation. You've got to be the arm.
The Canadarm, named after its country of origin, was a multifunctional tool used for many tasks aboard the shuttle. A simple, articulated arm may not seem overly impressive, but the unique physics of a weightless environment and the desire to minimize the launch weight of the space shuttle made for a very interesting engineering challenge. The entire 15-meter-long arm weighs just 430 kilograms, and despite being able to move 30 tons in orbit, it couldn't even hold up its own weight on Earth. The booms were made from low-weight epoxy graphite composite with 6 joints, 2 joints at its shoulder for yaw and pitch, 1 elbow pitch joint, and 3 joints at the wrist for yaw, pitch, and roll, for a total of 6 degrees of freedom of movement, exactly like your own arm. However, your elbow is only capable of about 140 degrees of pitch before your bicep gets in the way. The Canadarm's elbow joint rotational axis is offset by 0.15 meters to allow up to 160 degrees of rotation. Because the arm is working in a weightless environment, the motors don't need to be able to apply that much torque. Each motor could only produce 0.7 Newton meters of torque. With no friction in space, a small force can move any mass. It just depends how long you want it to take. In the same way, ion thrusters with thrusts of just 25 millinewtons could theoretically get a spacecraft up to light speed if it had enough propellant. However, the dangers of inertia are still real. If a satellite was moving quickly relative to the arm, it could easily bend and break the arm. So, delicate movement is the name of the game, and the motor can work in reverse to assist each joint's brake system. The loaded arm speed had a maximum speed of just 6 centimeters per second. The arm had a unique end fixture designed to grapple onto attachment points on satellites. However, because the Intelsat was never intended to be rendezvoused with, it didn't have any grapple points installed. So, the capture bar had an attachment point for the second stage rocket and had a grapple point, allowing the Canadarm to grab hold of it once it was securely attached. The grapple point is a simple metallic pin with 3 lobes at its base. This is all the arm needed to firmly grab onto the Intelsat. The end effector of the Canadarm used a naturally self-centering wire grapple system to hold on to this pin. 3 wires, each anchored at 2 points. 1 point is stationary, while the secondary anchor point is attached to a rotating ring. Once Bruce had maneuvered the arm over the grapple rod using the camera feed, this rotating ring would turn and ensnare the pin, pulling it to the center. The pin is then pulled inwards until the 3 lobes at its base lock into corresponding cutouts on the outside of the grapple ring. A simple but effective mechanism. With the satellite now secure, the 3 astronauts could get to work attaching the new second stage to the capture bar, which they did successfully, allowing the Intelsat to raise itself to geostationary orbit, where it operated for 21 years. STS-49 had another mission to complete, a test run of space shuttle building techniques, but with their time in orbit running out, that mission lost a day. Life support systems on board were supplied with enough gases for the planned duration of the mission. Spherical tanks in the mid-fuselage contained high-pressure oxygen and nitrogen, with 3 nitrogen tanks and 1 oxygen, used to create a breathable atmosphere of 80% nitrogen and 20% oxygen. Of course, carbon dioxide needed to be scrubbed from the air, and this was done by passing the cabin air through lithium hydroxide canisters located underneath the middeck. These solid canisters would react with the CO2 to remove it from the atmosphere and create water in the process. This was not a renewable solution, so every 12 hours the crew would access and replace these canisters through the hatch on the middeck bay. There were also oxygen and hydrogen tanks used for the space shuttle's power system, a fuel cell that reacted the hydrogen and oxygen to produce water and electricity. These powered everything on board and produced water in the process, but this water carried some extra hydrogen gas, so before the water could be used, it had to go through a process of degassing, which separates the hydrogen and dumps it overboard. It was now time to prepare for re-entry, and the first step was closing those payload doors. But on STS-49, another problem was encountered. The payload doors would not latch due to thermal warping of the doors, requiring some creative problem solving.
There's always 2 astronauts trained to do EVAs, and I was trained to do an EVA on my first flight, and that's for a contingency if, for example, the payload bay doors wouldn't close or latch all the way when you're on orbit. We have special tools where we could winch them closed and latch them all together. And matter of fact, on STS-49, after we had trouble getting the satellite to launch because of a different switch configuration, we got up there and the payload bay doors wouldn't close all the way. And so we thought, oh man, we need to go back out and do that. So your first attempt to fix something like that is the thermal loads on the space shuttle that you can imagine. You know, you're 200 degrees in the sunny side and 200 degrees below zero on the dark side. So a lot of times you'll get a little bit of oil canning effect or a little twisting of the fuselage just because of the thermal effects. And that's what we did. We went ahead and had the barbecue mode and we started. So
going to brilliant.org/real engineering or by clicking the link in the description. You can get started for free for 30 days, and the first 500 people to do so will get 20% off Brilliant's annual premium subscription.